Okay, so hello everyone, and welcome to our new topic, which is going to be about the policy cruise. So at the beginning, we're going to cover the theory and design, and then we're going to go through the two examples before we're going to go for the tutorial example for the week number 9. So we start first with the definition of the policy crew, and that I think that's something that you already saw. Policy crew are used for providing a linear motion in a smooth, uniform manner, which is going to be a sliding friction. So every screw actually going to have, when you're going to turn it, it's going to move. So you're going to change the rotation movement into a linear movement. And we're going to have the sliding friction to do the effect. So they are linear actuators that transform a rotary motion into a linear motion. Power screw are used for the following three reasons. First, to obtain a high mechanical advantage in order to move a large load with a minimum efforts. For example, what we have in the case of the screw jack. Also, to generate a large force, like what we have in the case of the clamp or the vise. Also, to obtain a precise axial movement, and that's what we use actually in the machine tool lead screw, like what we have in the CNC machine, for example, or even when you move the cutting tool in the when moving the tool post actually on the lathe machine. Uh, More examples actually can be found, like let's say some types of the 3D printers also have a lead screw to do the work. The efficiencies between 30% and 70% are obtained with a conventional power screws. On the other side, we have another type which called the bolt screw, which is going to do a rolling friction instead of sliding friction, have an efficiencies of above 90%. And we're going to cover that in the second part of today's topic. Three main types we have for the power screws. This square, the Acme or the trapezoidal type, and we have the buttress type. And this is actually what you have in these photos. The squares and the buttress threads are more efficient, requiring less torque, while the Acme threads are easier to machine. They're designed to convert a rotary motion to a linear motion, as we mentioned earlier. So if you can have a look for these three photos, you will see that basically, if I'm going to hold the push in the middle, or is going to be the nut, and I'm going to start to rotate the screw will move forward and backward. On the other side, we're going to hold the screw and start to rotate these nuts. The nuts will move along the screw forward and backward. So once again, these are the forms of the power screw threads, as we mentioned here, the square, the buttress, and the Acme thread. Actually, they have tables for the design, and they have standards. We're going to have a look at them later. So, operates on the classic principles of the screw threads and its mating nuts. Well, sorry, it should be this one first. If the screw is going to be supported in the bearings and rotated, while the nuts is going to be restrained from rotating, nut will be translated along the screw. And if the nut is going to be made an integral part of the machine, for example, the tool holder for the lathe machine, the screw will be drive the tool holder along the bed of the machine to take a cut. Yeah, and that's what we talked about earlier. That's the lathe machine, and that's the lead screw. And we have the carriage that carrying the tool post is going to be moving forward and backward according to the movement or the rotation of the screw. Just give me 1 second. I try to get my laser pointer just to show you this stuff here. Now, we come to the case if the nut is going to be supported and prevented from moving linearly while it's going to be rotating, the screw can be made to translate. And the screw jack uses this approach. Okay, you remember that in this example, we're going to rotate the screw. The nut is actually going to be supported, and thus the screw will go inside and backward and do the work. Okay, and these are the multiple examples we have. Now, the forces and stresses analysis of the power screw is very important to understand. Of course, the larger the screw is, the more power and more force it can produce. That's logic. Just imagine again to have a jack is going to be quite small, something like 1 feet length, and try to actually try to take the load of lifting a truck. It's not going to work. Okay, the diameter is small, cannot do the work. So the larger the diameter is, the more power it can produce. So the main parameters we're going to have first is going to be the basic measured diameter, the D, and we have the number of the thread per inch, the N. We have the pitch value, 1 over N, and we have the minimum minor diameter, the DR, and the minimum pitch diameter, the DP, the tensile stress area, the AT, and the shear stress area, the AS. And by collecting these parameters, we can calculate the area. If I know what are the diameters, I can calculate what will be the tensile stress area. If I know the force and the area, I can find the stress. And I can find the tensile stress if I get to know what is the shear stress area for my thread. So as for stress analysis on the screw, the safest approach is to compute the area corresponding to the minor diameter for the tensile or the compressive stresses. We have standard tables for the standard screws. This one is for the Acme standards, and this actually from the old mode book, table 71. You can see in the first column, we're going to have the nominal major diameter in inches, the thread per inches, or what we call the pitch value, is going to be 1 over N, the minimum minor diameter, the minimum pitch diameter, the tensile stress area, and the shear stress area. They are all in inches. We have the metric standard for that. Now for the new book, you can see that the table is going to be almost the same. Okay, so nominal major diameter, the thread per inch, the pitch value, the minimum minor diameter, the minimum pitch diameter, tensile stress, and the shear stress. And this table can go with the maximum nominal diameter to be 5 inches. So we have the range between 1/4 to the inch of the inches up to 5 inches. Now for the metric power screws, we're usually going to use the trapezoidal thread system similar to the Acme threads, slightly different thread form and made to metric dimensions. But the concept is going to be the same. So the table we have is 17.1M, which means metric, are examples of the power screws with a metric trapezoidal screw thread. So the major diameter can be ranged between 8 to 125 millimeters, which is almost 5 inches. And the pitch diameter given, the pitch value is given, the pitch diameter is given, the minor diameter are given, the tensile stress area are given. We are missing something here. We don't have the shear stress area in the case of the metric. And this is one of the deficiencies we have for these tables. Actually, the actual standard table does have the shear stress area. Anyway, we'll try to overcome this one by using the IP standards and then again convert the answers. Okay, so you can see that the range will go to 125 millimeter, which is almost 5 inches. So to study the mechanics of the power screw, we need to consider two cases. The first one is going to be the raising of the load, and the second one is going to be the lowering of the load. Now you'll say, what is the difference? If I'm going to raise the load, I'm going to have the force, which is the weight of the load, is going to be against me. I get to make it lowering. It's going to be the opposite way. It's going to help me to going down. Okay, so this is the main difference between the raising and the lowering. So the forces at the contact surface for the raising of the load, the P is going to be the force required. The F is the friction force. The F is the load to be moved, and the N is going to be normal force. So we consider that a new element on the mating parts are going to be a box that's moving. We need to push it with the force P. We're going to have the friction force right to resist that. the load is pushing the weight down, you get a normal force which is going to be perpendicular to the surface of this landing. The angle lambda is going to be very important to find the equilibrium of the forces in the x-axis and the y-axis. So the distance from the beginning of the thread surface to the end, we call the L, or the lead length. The distance from the beginning to the end of the thread surface horizontally is going to be the pi multiplied by the dp. Okay, or if we know it as the pi multiplied by the pitch diameter value. So after collecting these parameters, we're going to consider the equilibrium of the forces to the two dimensions. So we start with the forces to the x-axis. Or in general, the sigma of the forces should be equal to 0. We start with the x-axis. So what do we have in the x-axis? We have the P is positive. The friction force multiplied by the cosine of the lambda is going to be negative, and the N multiplied by the sine of the lambda is going to be negative. These are the forces which are going to be affecting on the x direction. The sine should be equal to 0. Now we're going to do the same thing in the y direction, okay? And in that case, we're going to have the friction force, sorry, the load is going to be negative, and we have the N multiplied by the sine of lambda is going to be positive, and the friction force multiplied by the sine of the lambda is going to be, oh, sorry, the lambda is here. Yep, the N multiplied by the cosine of the lambda, and this one is going to be by the sine of the lambda. Of course, we're going to multiply by -1, again, to achieve this equation. Now, the friction force at the point of the slipping is going to be equal to the coefficient of friction multiplied by the normal force. We know that. Now I can substitute that value in the equation, and I can find a new equation to give me the value for the normal force and the required force, or the force, the force P. Okay, so by rearranging and combining the equations will give me that the N is going to be equal to the load divided by the cosine of the lambda minus the coefficient of friction multiplied by the sine of the lambda. And the power required is going to be equal to that force multiplied by the sine of the lambda plus cosine of the lambda multiplied by F divided by the cosine of the lambda minus the sine of the lambda multiplied by the F. Now we can calculate the torque transmitted during the raising of the load to be given by the equation that the torque is going to be equal to the pitch diameter divided by 2. That's it. And I can substitute the equation of the P and find the new equation for the TU. The tangent of the lambda is going to be equal to the L that we found, okay, and which is the lead length, divided by the pi dp. So I can substitute that in the equation to find that the torque is going to be given by a new different parameters. That simplify the work of finding the sine and the cosine of the equation. Now, the torque required to raise the load up a power screw with a square thread. Remember that the previous one, if I get to go back to it, okay, that was the general equation. If I get to have the square thread, you need to know how much torque must be applied to the nut of the screw to move the load, and this will be given by this equation. Okay, so you can see that the torque is going to be equal to the F multiplied by the pitch diameter divided by 2 plus the lead plus pi F dp divided by the pi dp minus FL. The F capital is the force to be moved. The dp is the pitch diameter of the screw. The L is going to be lead of the screw, and the small f is the coefficient of friction. Once again, you have to remember that the lead is defined as the axial distance that the screw will move in one complete revolution, which is going to be equal to the pitch value. Right? So now we have everything. we need to move to the next step. I want to lower it. So during the lowering, you can see that the P and the F friction force are going to be exchanging positions. Now you can see that the load is going to help me to push the P downward. So the same parameters, the force required is P, the F is friction force, the F capital is load to be moved, and the N is normal force. We are going to consider the equilibrium of the forces. Forces to the x-axis are equal to 0, or the P minus the the friction force cosine of the lambda plus the N sine of the lambda is going to be equal to 0. You remember that in the previous equation that the P were opposing both the normal force effect and the friction force effect in the x direction. Now, the normal force effects in the x direction will support the P. Now, to the y direction, we're going to do the same thing. And obviously, we can see that the load to be downwarded is going to be minus the friction force sine of the lambda minus the normal force cosine of the lambda are equal to 0. Once again, the friction force at the point of the slipping is going to be equal to the coefficient of friction multiplied by the normal force. We're going to rearrange these equations again. We're going to find the equation for the normal force and the p value. Okay, you can see that the signs has been changed here. And then we can calculate the torque and the lambda. So the torque required. Once again, you can see that the sign has been changed here. And this will give me that the final equation to lower down a load with the power screw, the square thread, will give me the following equation. So what you can see that the main difference is in the previous equation, we had the plus, and here we have a minus. So anyway, if I'm going to show you the both equations, the TU, okay, is going to be equal to the FdP multiplied by the tangent of the lambda plus the coefficient of friction divided by 1 minus the F multiplied by tangent of the lambda. The TD for this one for taking the load up and this one to take the load down is going to have a different equation with the different signs here. The lambda is the lead angle that we set we can calculate by using the L and the dP. So now these are the two equations. The other one is taking the load up and the second one is taking the load down. Now we have something very important in the power screw. I don't know if you used the jack before that have the power screw, but usually when you turn it and a certain point is going to lock itself. Same thing when you do with the vise. It's not going to go back. So the force, which the load force is going to try to lock it, and that's what we call the self-locking. So if the screw thread is going to be steep, and this will mean that it's going to have a high angle, a high lead angle lambda, the friction force may not going to be able to overcome the tendency for the load to slide down of the plane. The load will be fall due to the gravity. So what to do? In most of the cases for the power screw with a single thread, however, the lead angle is rather to be small. And the friction force is going to be large enough to oppose the load and keep it from sliding down the plane. Such a screw is called the self-locking. The desired characteristic for the jack and similar devices. And that's what you can see in the GIF photo that I just added here. However, quantitatively, the condition that must be met for self-locking is that the coefficient of friction should be more than the tangent of the lambda. If I'm going to have this scenario, I can say that this power screw can be self-locked. Now, calculating the efficiency for the power screw. The efficiency is going to be equal to the work output divided by the work input, then the general equation for the efficiency. So it's going to be equal to the F multiplied by the L You know that the force by the distance is the power, or the work, sorry, and divided by the P force multiplied by the pi multiplied by the dP, which is the work again to input. Okay, and then the F divided by the P, or the load divided by the power of the force I added, multiplied by the tangent of the lambda, will give me the efficiency of the power screw. Alternatively, I can use the torque to do the same calculation. So the efficiency of the transmission of the force by power screw can be expressed as the torque required to move the load without the friction divided by the torque required to move the load with the friction, or the T divided by the T up, or TU. So by calculating the value for the T, it's going to be equal to the FL divided by the 2 pi, and then the efficiency will be calculated by multiplying by the force by the lead distance divided by 2 pi, and then multiplied by 1 over TU. So these are two different equations to calculate the efficiency in the case of the square thread. So not all the threads are square. We may have them as the Acme threads. So in that scenario, we're going to have the two different equations to calculate the torque for lowering or uh, uh, raising the thread. So this equation 1710 is for the torque required to raise the load, and the other one, TD, is also equation 1711, is going to be for torque required to lowering the load using the Acme thread. Finally, the power required to drive the power screw. If the torque required to rotate the screw is going to be applied at constant rotational speed n radian per second, okay, or revolution per minute, depend on what are the unit you are using, then the power in horsepower to drive the screw is going to be equal to the T multiplied by the N divided by 63,000 horsepower in the US units. The torque is going to be in pounds feet, and the N is going to be a revolution per minute. In the case of the SI unit, we're going to have the torque is going to be in Newton meter, and the omega is going to be in radian per second, or is going to be equal to the torque multiplied by 2 pi and divided by 60 if I would like to use the RPM value. So again, to solve one example here, the other example is going to be solved within the tutorial questions. The example 17.1 from Mode textbook on the torque and the efficiencies of the power screw. In this example, we have two Acme threaded power screws are to be used to raise a heavy access hatch. The total weight of the hatch is 111.2 kilonewton, or 25,000 pounds. They are divided equally between two screws. That means definitely that each screw I have is going to have half of that load, or 12,500 pounds, or the 111.2 kilonewton divided by 2. Select the satisfactory screws from the table 17.1 on the basis of the tensile strength, limiting the tensile stress to be 68.95 megapascal, or 10,000 psi. Then determine the required thickness of the yoke that acts as the knot on the screw to limit the shear stress in the threads to 34,475 megapascal, or 5,000 psi. Then determine for the screw thrust design, compute the lead angle, the torque required to raise the load, the efficiency of the screw, and the torque required to lower the load. Use the coefficient of friction to be equal to 0.15 as a unitless value. So now let's have a look on the case once again. It's actually to be that one. So once again, we have the table, or the moving yoke is going to go up and down, and is going to be carrying about 25,000 pounds here. Divide the load by 2 screws. These screws are using the Acme thread, and we need to find out what will be the diameter of that thread or the screw, and also the width or thickness of that yoke. And this will be related mainly to the area. So you don't have to worry about that. It shouldn't be something hard to understand. Once again, the load of 25,000 is going to be divided equally between the two between the two screws. That's a cross section of the work. Now the solution. First, the load to be lifted on each screw in direct tensions. Therefore, the required tensile stress area can be found directly. So the area mainly is going to be equal to. Now let's go back to the question. We had the force, which is the load itself, and we have the limiting stress. I will go back to the question again. So you can see that the limiting stress is given and the load is given, so I can find the area. If I go back, well, I know that I shouldn't do that, but if we go back to the first page, we start with the parameters here. The stress is equal to the F divided by the AT, or the AT is equal to the F divided by the stress. So I can find the AT. Okay, so this will be the first thing I'm going to do. Let's go back to the answer. And I just did that to show you that how we can start to do the solution. We need to have all the equations to be written in front of us. So now again, to find the required tensile stress area by knowing what is the force and what is the stress. So the AT is equal to the force, which is the load, divided by the maximum stress. And in that case, it's going to be equal to 111.2 divided by 2, divided by 68.95 megapascal. And this will be 806.5 millimeters square. Now I can get this value and go back to the tables. So back to do that once again, I will go to the tables. I will put the tables actually for you in the class within the example, so you can actually find the answers directly. So we said that we're going to have the 800 something. So now 36 knots, and it's going to be in the range of 921 here, and it was 754 here. So it's 36, 40, maybe 38 will do the job. Okay, 38 is not the standard, but anyway, we can take this number directly, and then we're going to do the solution, and later we're going to find the most appropriate one. So here we said that the 38.1 millimeters, or the 1.5 inch diameter on the Acme thread screw with 4 threads per 25 millimeters will provide the tensile stress area of 816.8 millimeters square. So actually, I can tell that here he used the IP units table. For this screw, each 25 millimeter length of the nut will provide 1,510 millimeters square shear stress area. And the required shear stress area in the nut is going to be simply calculated by finding the F divided by the tau d. And then I can find the value for the shear stress area to be 1,613 millimeters square. Okay, now we go back to find out where did we find the 34.4. Okay, so that's the shear stress we had. Okay, so that's how we found this value. We know we know this one, we can find the shear stress area. Okay, now the required length of the yoke in that case, H, is going to be equal to the shear stress area multiplied by the by 1 inch or 25 millimeter divided by the 1,510 millimeter that the type of the 38.1 millimeter diameter screw can provide for 1 inch. Okay, so we can find that the height is going to be 27.18 millimeter, or a little bit more than the 25.4 millimeters. Well, cutting is going to be done. First, the price length of the yoke is 27.18 or 1.07 inches, and thus we can choose the 1.25 inch as a value. The lead angle now can be calculated, which is going to be equal to the L, which is 6.35 divided by the pi dp, which is the pi multiplied by 34.11. How we got these values? We simply just got them from the table 71. Now, the torque required to raise the load, okay, or that's how to find the L, is the P, was going to be 1 over N, and this will give you 6.35 millimeters. Now, the torque required to raise the load is given by the equation that we derived earlier. Sorry. Now we know the F, we know the dP, we know the phi, the lambda, the F. Okay, and we can apply these equations, and then we will come to the answer that the torque here is going to be 204.4 Newton meter. Now we can calculate the efficiency by using the efficiency equation, and we can calculate the load required to lower the load. So that's it. This was actually just the trick was about how we use the load and the maximum stress to find the area, the tensile area. We did the same thing for the shear area, and then we selected the type of the screw that we need to use, and then we start to calculate other stuff like the L. We calculated the yoke thickness, and then we calculated the torque to raise the load, and then we found the torque to lower the load, and we found the efficiency. So you can see that this efficiency was quite small, 27.5, and it's something to be expected in the case of the power screw. Now for the torque, you can see that the torque to lower the load was 89.5, while this torque was 204.4. And that's mainly what I told you earlier, because when you lowering down, the load will help you to lower down the power screw. Now we can have another equation, another example, which using the same equation. So now for the same example, 17.1, it is designed to raise the hatch to a total value of 15 inches or 381 millimeter in no more than 12 seconds. We need to compute required rotational speed for the screw and the power required. If I get to have time to be involved, that means I can simply find the velocity. When I find the velocity, I can find the power. Okay, so how we can find that? How we can find the velocity? Mainly, we are going to have a distance to be moved, and thus we can find by using the pitch value, we can find how many revolutions per minute that this screw will be moving. And thus I can find the omega by using the conversion equation. So you remember that the screw we selected for the example problem 71 was 38.1 millimeter. You can use the 80, by the way, if you're using the SI units. Okay, so the fourth thread we have per 1 inch or per every 25.4 millimeters, and thus the load will be moving by a quarter inch or 6.35 millimeter with each revolution. Now I can know what the number of the revolutions. Okay, and I can find what will be the linear speed. we're moving for 381 millimeters within 12 seconds. So that means that the linear speed required is going to be 381 divided by 12. Or this will give me 31.75 millimeters per second. Now, rotational speed can be calculated by dividing by this velocity by the r value, or 31.75 millimeters per second. And each one revolution will give me 6.35 millimeters. And thus, I'm going to have 31.41 radian per second. Now that's it. I know the torque to raise the load is 204 Newton meter, and I know the omega now. I can find the power to be equal to 6.421 kilowatt. Okay, so that's it for the introduction session, and we're going to go to the example in a separate video.